Kia ora, Year 13, and welcome to a lesson on Type 1 and Type 2 errors. This is a continuation of our hypothesis testing using binomial distribution. So today we'll be looking at exercise 8D, and the things that I refer to will be on page 196 of the red textbook, all the way down to 200. Okay, there's 4 questions for you to have a go at with these. So, the first question is, what is a type 1 and a type 2 error? If I draw you a distribution, and I'm not going to draw it symmetrical because we're looking at binomial. However, type 1 and type 2 errors do apply to normal distribution as well, and we'll talk again about this when we look at normal distribution. But basically, a type 1 error is where there has not actually been a change in the statistics for probability of something happening, but you end up rejecting your null hypothesis and accepting your alternative hypothesis. For instance, if we were looking at a one-tailed test at like a 5% significance level, if, for instance, we're rolling a dice. Here we go. We're rolling a dice, and it is not biased, and we're looking at the number of ones rolled. Okay. If you accidentally end up rejecting your null hypothesis that the probability of rolling a 1 is equal to a 6th, and accepting an alternative hypothesis such as rolling 1 is greater than a 6th, that would have occurred by falling within this crit region. Okay, when you fall within that crit region, you reject your null, accept the alternative hypothesis. A type 1 error is when this happens, but there has been no change. Okay, so when you accept alt hypothesis, but there has been no change. And it's not your fault that this happens. It's not like when we say type 1 error, it's not that you've made an error, it's that the statistics you've been given, the data you've been given, is showing that there has been a change when there hasn't. The other error that you may end up with is called a type 2 error. So if a type 1 error is where you accidentally reject your null hypothesis and accept your alternative hypothesis, I think a few of you might be able to work out what a type 2 error might be. So a type 2, actually they're not written as type 1 and 2, they're written as Roman numerals, it seems, quite often. So type 2 error is when you accidentally is when you don't have enough statistical data to reject your null hypothesis, so you accept your null hypothesis. However, there has actually been a change in the probability of something happening. So accept null. Okay. So it's when you accidentally end up in this green region when there has been an actual change to your probability. So for instance, the dice was biased. Okay, so if I have the dice and I'm looking at rolling 1s and the probability of rolling 1 is a 6th, that would be my null, and my alternative would be greater than a 6th if I'm talking about the dice overly favouring the 1. Then if the dice was actually biased and it does overfavour 1, but there's not enough statistical evidence in the data for me to reject my null hypothesis, that would be considered a type 2 error. So that is when you accept, I can't spell accept for some reason, null hypothesis, but there has been a change And it's explained quite nicely in the table that you have on page 198, which goes through the 4 outcomes of doing a hypothesis test. Okay, either the null hypothesis is true, and you get the correct decision to accept your null hypothesis because the statistics have pointed you in that direction, and you get a correct decision. Or if the null hypothesis is false and you correctly reject your null hypothesis, you get a correct decision. However, if a null hypothesis is true, but you end up rejecting it because you've ended up in that critical region with your data, that's called a type 1 error. Or if a null hypothesis is false, but you end up accepting your null hypothesis because there's not enough data to suggest there's been a change, that is a type 2 error. Okay, so that's basically the 4 outcomes. And you may be asked to do certain things with this, so let's actually have a look at a question which involves these concepts. So here's a question about a scientist who is looking at a certain species of moths. 6% of those moths are known to be red, and the rest are yellow. Okay. However, this scientist comes across a group of moths, another group of moths, and she observes that seemingly they are more red than she would have expected. Okay, so she's going to design an experiment in which she's going to catch 10 of those moths at random, look at their colour, release them, and then she's going to carry out a 5% significance level test to decide whether she is correct in saying that there's more moths than she would actually expect. Okay. So, first thing we're going to do is write our null and our alternative hypothesis. So, H0 is probability is equal to 0.6, which is the how to put this? There are let me rewrite this. The probability of a moth being red is 60%. That's probably the best way to write it. H1. So with H1 we need to decide if this is a one-tailed or two-tailed test. So was there ambiguity or was there direction? So because she said it was more than she would expect, there is a direction to this. So we're looking at just the greater side. There's not the ambiguity of, oh, there's not quite the same number of red moths as she would expect, you know, neither less nor more, but there's a direction here. So we're going to do probability is greater than 0.6 because more. So the probability of a red moth, of a moth being red is more than 60%. That's in this new colony anyway. In the new colony. Same far above. So in the new colony would go up here. Because you're not talking about all of this kind of moths, you're just talking about this specific group of this kind of moth. Okay, so that's part 1. That's what you'd write. Part 2, finding our rejection region. So let me just draw a quick distribution for this. So it's 60%, so it's going to be distributed to the right. Okay. So we're wanting a 5% significance level, the rejection region. So we've tried to find that crypt value where anything above it is under 5% of our distribution. So we're trying to find this region here, okay, of a value which pertains to that region. So we're going to do binomial distribution to work this out using the assumption of 0.6 and the number of tests being 10 because that's how many moths she will be catching. So there's 10 moths with a 0.6 probability of distribution. and we're trying to find 5% significance level. So I'm going to start off on the far right side because we're looking at that end on the right side. So I'm going to look at the probability that x is equal to 10, just that top end value. Okay, so I would type that into a calculator, which would be 10c10 times 0.6 to power 10, and you can type in 0.4, so times 0.4 to power 0. Okay, so 10c10 times 0.6 to power 10 times 0.4 to power 0. You don't actually need the 0.4 to the power 0 because it's 1. You don't even need the 10c10 because that is also 1, so technically you only need the 0.6 to the power 10, but it's just good practice to write the whole thing. And that gives you a probability of 0.00605 to 3 significant figures. Okay, so that's not significant enough. So that would be significant enough. If there was exactly 10 red moths in a sample, we would reject that region. But we're trying to find the lowest number of red moths you would need to be able to reject your null and accept an alternative hypothesis. So now we're going to look at the probability that x is greater than or equal to 9. So remember, we're including 10 in this. So we're going to take our 10 value and add our 9 value to it. So 10c9 times 0.6 to power 9 times 0.4 to power 1. Again, do that on a calculator. So if you've already got the previous value, it's good to keep that previous value stored as the answer, and then you can just add on your 10c9 times 0.6 to power 9 times 0.4 to power 1, which gives you 0.0464. So that's very close to our 5%. It's still within that region, within that 5% region. However, it's likely that our next value is going to take us out of that. So if I do the probability x is greater than or equal to 8 and take 0.0464 to 3 significant figures and add our 10c8 onto that, so again, if you've got this on your calculator and your previous thing is the answer plus the 10c9 one, you can just go in and alter your powers. So 0.4 squared, 0.6 to the power 8, and 10c8. It just makes life a bit quicker and easier. And you get to your answer of 0.167 to 3 significant figs, which means that that is now outside of our critical region zone. So the crit region is x is greater than or equal to 9. Okay, so the rejection region is x is greater than or equal to 9, which means that if the number of moths number of red moths, not just any old moths, specifically red moths, is greater than or equal to 9, you accept the alternative hypothesis. Okay, so that's part 2, finding our rejection region. The next part 3, says find the probability of a type 1 error. Okay, so remember what a type 1 error is. A type 1 error is where you've accidentally accepted your alternative hypothesis when you should have accepted your null hypothesis. So that only happens when you land within that crit region here. And actually you've already worked out the probability of this happening by trying to find that crit value. So the probability of that happening is the 0.0464. Okay, so your solution for part 3 is the probability of a type 1 error is 4.64%. Okay. With normal distribution, the probability of a type 1 error is the significance level. Okay. Because with that data it is continuous, and we'll talk about that later when we focus more on the normal distribution. But with binomial distribution, it's really important that you get the exact probability of the value, because it's discrete data. So you've got to take that discrete value and find out the probability of that happening. So this gets more confusing when we introduce normal later, but it's very important at this point that you understand it is from that crit value probability. Okay. Part 4 says, if in fact the proportion of red moths is 80%, so if in actuality there is a different proportion of red moths, okay, as in we should be accepting our alternative hypothesis, find the probability that the test will result in a type 2 error. Okay, so this is more complicated and requires doing some more math. So as part 3 was just, using what we've already calculated. Part 4, we are going to actually need to recalculate some values, okay? Because we've actually got a new distribution here. So a type 2 error would occur if the number of red moths was anywhere in that zone, okay? Which we know to be 8 or less. If the number of red moths is 8 or less, then you would have accepted, your null hypothesis, and you'd have rejected your alternative hypothesis. So when we look at our new distribution, because we know the probability actually has changed, we need a new distribution. Okay, that wasn't a great drawing. And our BMP is now B10 0.8. What you are trying to find is the probability of getting 8 or fewer red moths. 8 or fewer red moths. What is the probability of that happening? Okay, my distribution might not be quite accurate for this situation, but it is what it is. Okay, so we try to find out this percentage of 8 or fewer red moths. The best way to do this is just to do 1 minus your 9 and 10. So that's what we're going to do. So we're going to do the probability that x is less than or equal to 8, which is 1 minus the probability of 10. Also, 1 minus the probability that x is greater than or equal to 9. So probability of 10 plus probability of 9, which is 1 minus 10c10 times 0.8 to the power 10 times 0.2 to the power 0. In fact, I'll put a bracket around that. Plus 10c9 times 0.8 to the power 9 times 0.2 to the power 1. Type that all into a calculator and you get the answer 0.624. So the probability of a type 2 error is 62.4%. The probability of a type 2 error is 62.4%, which is quite high. Type 2 errors actually occur quite often because our significance level is so small. Like, we need to be really certain to reject a null hypothesis. Okay, there's got to be a lot of statistical evidence to reject a null hypothesis. So type 2 errors happen quite frequently because the probabilities have actually changed, but there's not enough evidence to accept that there has been a change. Okay, so they do tend to be quite high numbers. So all I did there, just as a recap, is we accepted that there has been a change, the 80% value, and then we inquired as to the crit region, or the opposite of the crit region. If a crit region is 9 or more, the uncritical region is 8 or less, so we used our uncritical region 8 or less to test for type 2 error, using the values of 1 minus probability of 9 or more as our way of finding that. Okay, hopefully that explains enough for you now what a type 1 and type 2 error are. If you have any more questions, please do send those questions through. I can answer them. I've already answered 2 today, so if there's any more, please do send them through. Hope you're all doing well, and I hope to speak to you again soon. Bye.